All right, friends. Now what we're going to discuss are called heaps. These are binary trees, but they are not binary search trees. They organize their data quite differently from binary search trees. So with a binary search tree, you have a node, and then any node to the left is less than that node, and any node to the right has to be greater than it. The heaps, the definition are a complete binary tree, not binary search tree, but a binary tree, whose nodes contain comparable objects and are organized as follows. Each node contains an object no smaller or larger than objects in its descendants. Now, the smaller or larger doesn't mean you get to pick always willy-nilly. There are actually two different types of heaps. You have to decide whether your heap is a max heap or a min heap. If it is a max heap, the object in the node greater than, an object in the node has to be greater than or equal to all of its descendants. Both sides, not just its left, not just its right. It has to be greater than both its children, and then each of its children have to be greater than their children, and so on. So a min heap, the object in the node is less than or equal to its descendant object. So that means that in a min heap, the nodes will be smaller as you go up toward the root. So here's an example here. This right here, we have a max heap and a min heap. The max heap is on the left. We see that at any point, the node at the top here, 9, is greater than both of its children. And then at 8, it's greater than both of its children. And 6 is greater than both of its children. 7 is greater than both of its children. On the min heap, it's the opposite. This node is smaller than both of its children. This node is smaller than both of its children. This node is smaller than both of its children. And this one is smaller than both of its children. So there are actually two properties that you have to maintain when you have a heap, and as you build the heap and as you remove items from the heap. The first property that you have to pay attention to is the structural property of the heap. Heaps, no matter whether they are min heaps or max heaps, have to be complete trees. That means that if you notice here, they are full up to the second to the last level, and that they are filled in as far left to right as possible. So if I added another node, it does not matter what value is in it, I would add the node here on both trees. Then you have to perform operations to make sure that the nodes maintain what's called the heap order property. Meaning if I inserted, for example, into this tree right here with 9, 8, 6, 7, 3, 2, 5, 4, 1, 4, if I inserted, say, a 12, then the 12 would initially go here, or at least we would put the node here for the 12, and what would happen is we would say, wait a minute, did I maintain the structural property? And you would say yes, because now it's still a complete tree, but have I maintained the heap order property? And the answer would be no, because 3 is definitely not larger than 12. So you would swap 12 with the 3 would move down here, the 12 would move up, then you'd compare 12 and 8, 12 with its parent, you'd swap those, and then 12 with 9, and 12 would actually move up into the root, the 9 would go down here. So that's how we would maintain the heap order property. We are going to do an example. I think they're just giving a little basic code example. Oh, and another thing about heaps is that they're one of the best implementations of a priority queue. Before, when we talked about priority queues, we talked about, well, what about sorted lists and unsorted lists? Well, with an unsorted list, it's really nice because you can just add items really easily. So that's big O of 1. You can add it to the end or the front or wherever. But when you have to locate the item that is the maximum or the minimum, meaning the one with the highest priority, then you have to actually search the list. So that's big O of n. So that's kind of bad. And then the opposite's true for a sorted list. To add an item, it's big O of n, because you have to find the right location for the item. But to retrieve an item, a max or a min, you know that the max is always going to be at the end, or the min is always going to be at the end, depending on how you organize it, because it's sorted. And so you still have the big O of 1, big O of n, but they're just switched. So a heap actually is the best, in practice, option for the priority queue implementations, and sometimes people actually make them, or rather, sometimes people use the terms synonymously, priority queue and heap, because they're so intertwined and so used for each other. So the heap is good because it has a log of n It has actually a constant retrieval time. It's very simple to actually get to the minimum or maximum because it's always at the top. So you can always know who's next when you get the item at the top. So we don't get to arbitrarily remove items from a heap. We have to remove min or remove max, and that's basically how a priority queue functions. So we'll take a look at this in just a second. There's other types of trees as well. This is like a game tree and things like that. How do computers know how to play games and know how to place items on chessboards? They create, or at least create, partial trees and then eliminate portions of the tree using what's called pruning. Okay, pruning should make sense because that's what you do to trees, right? So it removes part of the search space. Algebraic parse trees, all kinds of different trees. So we will talk a little bit about implementation, but we're going to go through and discuss, I guess we're going to open that first, but I'm going to go over to Paint, and we are going to discuss the heaps. So let's come up with some numbers. I'm just going to kind of randomly, semi-randomly come up with some numbers here. 13, a 2, a 9, 15, we'll say 21, 7, and 18. Okay, let's say we want to build a max heap. So this is a max heap, and we're going to add these items one at a time. And then we're going to fix it basically based on where the item should go. So the first item we add to our max heap is, oh geez, this thing's malfunctioning. Does that sometimes. Sorry about that. Oh, still doing it. It's very, very sensitive. Let me see if I can get it to not do that. Okay, this thing malfunctions a little bit occasionally, so I had to take a little bit of a reprieve. It starts getting very sensitive. Okay, so 13, we add that to our max heap right here. There's the first node. And then we add a 2. And remember, we first worry about the structural property. So structural property, that's whether it's complete or not. And then we worry about the heap order property, heap order. Okay, so we've got the 13. We have a 2. We always add it to the left here, and then we fill it into the right, and then you go down and you keep trying to make it a complete tree each time, and then you worry about the heap order property. So I've added a 2 here, and I've got the 13 at the top. And then I have to ask the 2, hey, since this is a max heap, are you bigger than your parent? And the answer is no, so it doesn't do anything. And now I add a 9. Again, completely not paying attention so much to the heap order yet. We worry about structure first, so we keep it a complete tree. We have a 9 here, and then once we've done that, ask it, are you bigger than your parent? And the answer is no. Now we add a 15. To maintain the structural property, we add the 15 here, and we first ask, are we a complete tree? And the answer is yes, we're good. But what about the heap order property? And the answer is no, we are not good. So we have to do what's called heap up in order to restore the heap order property. The 15 goes up to here, and the 2 swaps with it. And then when the 15's here, it'll ask again, am I bigger than my parent? And the answer is yes. So that would cause that to happen. So I'm going to redraw it, and then I'll erase the original one. So the 15 will end up at the top. It will have a 13 to its side, and then a 2. And then the 9 did not move at all. So I'm going to have that. I'll move that guy out of the way, kinda. 1 second. It's parent selection, and we'll move him over kind of right there. So this is our active tree that we're working with right now. Sorry, 1 second. All right, so that's our active tree. So we have the 15. Now we ask, what about the 21? Well, you again maintain the structural property first. So I have a 21 there. And is it a complete tree? And the answer is yes, because it's filled up to the last level and filled in from left to right as much as possible for the number of nodes we have. And then we have to ask, am I bigger than my parent? The answer is yes in this case, so I have to heap up and then move the 13 down. And then the same thing is true about the 15. So now this is actually going to transmit into this tree. It's going to turn into this tree. So we have the 15 on that side. The 9 has not moved. So 15, and then the 13, the 2 hasn't moved either. And then the 13 has moved there. Okay, so we 15, 13, 9, 2, 21, 15, 13, 9, 2, 21. There you go. And we have restored the heap order property, because you'll notice that the 2 is less than the 15, 13 is less than the 15, 15 is less than 21, and the 9 didn't move. So that's called heaping up. Again, I will move this guy off to the side. We would have normally just erased the value in between, but I'm just kind of showing some progress here, what we're doing. Let's do this. There we go. So that's our active tree right now. Now I'm going to add a 7. So I add the 7, and the 7 goes as the left. Here we go again. Okay. 1 second. Okay. All right. I'm going to move that over again. Sorry about that. Okay. Now, back to that. So we add the 7 to the side here, and we've maintained the, so 21's there, 7's there. We ask if it has maintained the structural property, and the answer is yes, because it is a complete tree, full up to the second to the last level, and then filled down here. And then we add the 18. So we put the 18 here, and then we say, okay, well, is the structural property maintained? The answer is yes. What about the heap order property? Nope, that has been violated. So, because the parent is smaller than this. So we move the 18 up here, and then the 18 asks, am I bigger than my parent? And the answer is no. So now we actually get with the final tree, we have a 21. The one side doesn't change. 15 to 13, 9, and then 7 and 18. Oops, sorry, the 8. Sorry, let's fix that. 18 goes here, then the 7 is on that side, and the 9 has swapped places with us. So that's what we've got for that. Now, one other thing to note is what happens when I remove something. How does removal work? Well, removal, you might think I can just arbitrarily remove whatever I want. The answer is no, you can't. So to remove an item, you actually only remove, you can call removeMax. So I have an algorithm called removeMax or removeMin, depending on if it's a min or a max tree. If it's a max tree like this one, we are allowed to call removeMax. And if it's a min tree, we can call removeMin. So what happens if I remove max, and it will give me a 21, so I return the value 21 right there. But what to do with this node? So you might think, okay, let's delete the node, and then we can do a little bit of manipulations here and everything will be fine. And we could try something like that, but that's not how it's done in practice. In practice, we're not really concerned about the node being removed. We just want the reference to the value to be removed. So what we do is we actually, to maintain the structural property again, which node would we want to get rid of? Actual node, and to remove it. And this is actually the answer right here. I would want to get rid of this node, but I don't want to lose the value, so I just copy the value up here. So if I delete this right here, right there, and put my 9 up there, and get rid of this node down here. Let's see if that looks good. Okay, not too bad. Now, so have I maintained the structural property? The answer is yes. And what about the heap order property? And the answer is no. Actually, it's been violated now. So now you have to do what's called heap down. So when you remove, you have to heap down. Okay, when you add, you heap up, typically. So what we're going to do is we say, hey, I'm a 9 and I want the maximum to be up here. So which of my children at this point is bigger? And the answer is 18. So I'm going to move the 18 up and the 9 down. And then I look at both if there are 2 children and say which is bigger, and you continue like that recursively. But since the 9 is actually already larger than its child, then it will just park right there. So I'm going to get rid of those arrows, and we are going to, I guess, erase the 9 here. This is very sophisticated. Okay, sorry, 1 second. This drawing pad has a mind of its own. Okay, so the 18 and the 9 swap place. 18 and the 9 swap places. 18 goes up here, 9 goes out there, and we have removed the value correctly, 21, and put the rightful new maximum in place. If we call removeMax again, so let's say we call removeMax again, we get an 18 right here after the 21, and then what happens, what do I swap with? I swap with the 7, or rather remove the 7, or remove the 18 value, and then we're going to remove the 7 node itself and just put the node up near the top. So that's basically what we want to do. 7 goes up here, but then we have to say, oh wait, do I belong here? And the answer is no, it has to swap with the 15. So I have to get rid of this, move the 15 up, because that's the larger of its 2 children. And then I'm going to move the 7 down. So the 15 moves up, and then the 7 moves down. And then you ask again, am I larger than both of my children? It is larger than the left child, but not the right. And if both of its children were bigger than it, you would go with the larger one, like we did just a second ago. But this one, we want 13. We want 13 to swap places with the 7 to restore the heap order property. So I'm going to put the 13 right here and put the 7 right there. And you could keep going, and you'll notice that I would get 15, 13, 9, 7, 2. And you'll notice that this is actually sorting it. It's actually sorting. It's in reverse order, but that doesn't really matter. We could put it in an array of the same size as this, or a linked chain, and do it backwards. It doesn't really matter, right? But this is very interesting, and the fact that we can remove the max or the min, actually get the value in big O of 1 time, and we have to do the reheaping in big O of log of n time. That means we can do a sort. If we call removeMax, which is log of n, ultimately, it's this actually getting the value is only big O of 1, but the actual reheaping and everything is log of n. We do it n times, so that's n times log of n. So we get n log n as the big O to sort it. So that sounds like that's just as good as any of our other n log n, like quick sort and merge sort that we saw before, and that is what it is. It is called heap sort. It's a sort you use a heap for. I told you we'd hold off on it when we talked about sorting, and I did, and we have it right here. So I'm going to actually save this to make sure we keep it. We'll call this Heaps. Okay, and we now have, oops, sorry, wrong button. Tree implementation. So we'll talk very briefly about this. I'm not going to go through the whole thing. I'm just going to give you kind of an idea of the first few slides. So whether we have a binary search tree or a regular binary tree or a heap or anything like that, we do go back to the basics, and we have this type of structure. So the nodes look very different, or not very different, but they look similar but different to what you would have in a linear structure. You will notice that the node has a pointer or reference to the data object, which we would normally have, but you actually have 2 references, and we don't have next previous. It has reference to right child and reference to left child. So you'll see that each node would have this, so they would be able to recursively create some tree. So it looks something like this. A binary node, this is the node, not the full tree. The node contains data, and it also has a reference to a left child and right child to another binary node that holds a t. You'll notice that this, to start with, we have the data portions. We got several different constructors: set data, get left child that just returns the child and such. Now, once we get to the actual binary tree, we have a binary tree interface that it has to implement to be able to set the tree. The class binary tree has a root, which is a single binary node, so it just maintains the root, just like a linked chain or something like that would maintain a reference to the front node of the first node. So this one maintains the root maintains each of its children, and by default each of its children are set to null. So every new node added is a leaf to start with, but it can obtain children later on as you add items. So I'm not going to go through the whole thing, but you can see there is a lot of recursion built in. It's actually quite difficult in some ways to do some of these algorithms iteratively, so a lot of times they are left recursively. So we have talked about the fact that recursion is not always the most efficient way to do things, but as far as coding them and making them work elegantly, a lot of times that is what you're going to do with a tree structure. Okay, linear structures, we usually have a really good iterative option as an alternative, but with tree structures, not as much. So that's pretty much it. I'm not going to go over specific binary search tree implementations. So we're actually done with this week's lectures. Thanks very much, and I'll see you for the final lecture on graphs coming up.